Okay, last video of the course. All right, in a water environment, water itself will split up into ions. H2O can split up into H plus and OH minus, and there is an equilibria that is constant for this. In other words, all water environments have some H plus particles in them. Normally we would think of H plus as an acid, but really all water environments have some acid in them. All water environments have some base in them because all water environments have some water molecules that split up and produce H plus and OH minus. Now, when the H plus dominates the solution, we call the solution an acid. And when the OH minus dominates, we call it a base. And when they are equal concentrations to each other, then we say that they are neutral. But there's always some H plus in a water environment. There's always some OH minus. That ionization we call Kw. Right, the equilibria for that ionization. So it's going to be H plus times OH minus, and it always comes out to be 1 times 10 to the minus 14, so it's a very small number. And you don't have to memorize that number. That number will be given to you, of course, on a test. So, Kw, left off there. All right, so Kw is H plus times OH minus, and that's always going to come out to be 1 times 10 to the minus 14. So let's say, for instance, when I said the H plus dominates, it's an acid, with the OH minus dominates, is considered a base. What if they're both equal? If they're both equal, then this would have to be 1 times 10 to the minus 7 molar times 1 times 10 to the minus 7 molar in order to multiply out to be Kw if this was a neutral solution. Notice that negative 7. Does that number look familiar to you? Does the negative 14 look familiar to you? It should, because if we had a neutral solution, we would say the pH of that solution is equal to 7. In other words, if we take the base 10 log, pH is going to be equal to the base 10 log. Now, you don't have to know, some of you have had algebra 2, some of you haven't, what a base 10 log is. You just have to be able to find the LOG button on your calculator. So pH is going to be the negative log of the H plus concentration. So I should put that in brackets. Sorry about that. All right. So let's say something is an acid and has a pH of 2. Then we would know that the H plus concentration would be 1 times 10 to the minus 2 molar. That's what that 2 represents. So therefore, the base concentration, if this is going to multiply out to be 10 to the minus 14, would have to be 1 times 10 to the minus 10 molar. I'm sorry, 1 times 10 to the minus 12 molar. So notice something here, that this number 14, we said the pH scale in middle school, they told you pH scale was from 1 to 14. That's where that number is coming from. It's coming from the Kw value. So again, if the pH is 2, then the OH minus concentration, again, would have to be very, very small. They don't have to be equal to each other. All right, so questions they would ask you on a test. Hey, what's the hydroxide concentration in a solution where the acid concentration is 1.5 times 10 to the minus 6 molar? Okay, a couple of ways we could do this. We know that H plus is equal to 1.5 times 10 to the minus 6 molar. And we know that Kw is equal to H plus times OH minus, which is 1.0 times 10 to the minus 14. So we can solve this for OH minus. Kw over H plus. Again, in equilibria expressions, we don't worry about the molarity unit, because technically the molarity unit for Kw would be molarity squared. I mean, I've seen it in some textbooks. They do that, and then this cancels, and you wind up with molarity. But as a standard practice, they really don't include the units in these calculations. 1 exponential negative 14 divided by 1.5 exponential negative 6. So that gives me a concentration of 6.7 times 10 to the minus 9. All right. Well, here's another way you could do it. We know that pH is equal to the negative log of the H plus concentration. So what is pOH then? Well, pOH is the negative log of the OH minus concentration. So on the pH scale, an acid is anything less than 7. On the pOH scale, a base is anything less than 7. On the pH scale, an acid is greater than 7. On the pOH scale, an acid, did I just say, man alive, the pH scale, the base is greater than 7. On the pOH scale, the acid is greater than 7. But pH plus pOH always comes out to be 14. So another way they could approach this problem is they could say, all right, instead of giving you 1.5 equals 10 to the minus 6, suppose they gave you the pH instead. So the pH for this would be 5.8. So if they gave us the pH instead of the H plus, and they said, all right, here's the pH of 5.8, what is the OH minus concentration? Well, then we could say, all right, pH plus pOH is equal to 14. pOH is equal to 14 minus pH, which is 14 minus 5.8. So the pOH is equal to 8.2. Now, how do you go from pOH to OH minus? If you haven't had algebra 2, the OH minus is going to be the inverse log of 8.2. So you would do 10 to the 10 to the negative x. So find your log button on the calculator. If you go to the shift function, it should be over, the log should be a 10 to the x key. And I'm sorry, not negative 10 to the negative x, 10 to the negative pOH. All right, so we're looking for the 10 to the x button here. And we're going to put in 10 to the negative 8.2. And we get 6.3 times 10 to the minus 9. Now, why the difference? The difference is in the way the sig figs are applied. Remember in the beginning of the year we were talking about sig figs for multiplication and division is different than addition and subtraction. Sig figs for logarithms is different than sig figs for multiplication and division. The difference between the 6.7 and the 6.3 is how the sig figs were applied. Technically, when I did pH 5.8, it should have been like 5.82. It should have been an extra sig fig. Any event, let's go back to the easier questions. All right, so we said pH measures the acid concentration. So if they give us H3O plus, that's the same as H plus. And so do negative log of H3O plus. It's not a formula you have to remember. It'll be given to you on the test. And we said on the pH scale, numbers go from 0 to 14. 7 is neutral. Less than 7 is an acid. Greater than 7 is a base. What is pOH? pOH is the negative log of the OH minus concentration. So instead of measuring the acid concentration, we're measuring the base. The smaller the number, the more basic it is. So numbers less than 7 on the pOH scale are bases, greater than 7 are acids, the opposite of the pH scale. And then pH plus pOH is equal to 14. Nothing that they want you to know about the pH scale, since it's based on a scale of 10, that a one level change actually represents 10 times as much change in the acid. So for instance, pardon me, if a habanero pepper had a pH of 2 and battery acid was a pH of 3, that means that the habanero pepper is actually 10 times more concentrated in acid than the car battery. And if a jalapeno had a pH of 4 and We had neutral water at a pH of 7. That's a difference of 3. So 10 to the third, we would say that the jalapeno is 1,000 times more acidic than neutral water. Okay. I said once we did pH, I would do a calculation with Ka. And then our last thing is titrations, and we are done, folks. All right. Suppose they gave you this information. Let's say we had acetic acid. And they say, all right, here's the dissociation of acetic acid in water. It produces H+, it produces CHCO3-. And they said, we let this go to Equilibria, and we find that we have a pH equal to 2.67 and a Ka equal to 1.8 times 10 to the minus 5. They want to know, at Equilibria, what is the concentration of H+, what is the concentration of CH3COO-, and what is the concentration of the original molecular acid. So in other words, all three species. Okay, well, first of all, the H+ is pretty easy to do because they gave us pH. And again, if we know pH, we can get the H+ concentration. So pH is equal to 2.67. The H+ concentration is going to be the inverse log. So find the 10 to the X button and type in 10 to the negative 2.76. And we're going to get, I said 2.76, 2.67. And we get H+ equal to 2.14 times 10 to the minus 3 molar. So we can put that in. Okay. So if we know the H+ concentration, look at the mole ratio here. We don't have any other interfering material. So the only thing that's in solution is the acetic acid. So for every X moles of H+ that's produced, we also get X moles of acetate. So now we have a molarity. They don't tell us the volume, but it doesn't matter here. Molarity, they're in the same container, so they're going to have the same volume. So if they have the same X amount of moles, then therefore they have the same molarity. So since both of these are equal to X, both of their concentrations are 2.14 times 10 to the minus 3 molar. Now the last part, a little bit of algebra. We know that Ka for this is going to be ionized acid times conjugate base over original molecular acid. And we know that the Ka for this is 1.8 times 10 to the minus 5 because I told you so. All right, so let's solve for CH3COOH. And this will be H+, which we already know, times conjugate base, which we already know, over Ka. Okay, so now we can substitute in. Both of these are 2.14 times 10 to the minus 3. So I'm just going to write 2.14 times 10 to the minus 3 squared and put that over 1.8 times 10 to the minus 5. If I insulted some of you mathematicians, forgive me. I probably didn't have to tell you that. All right, so 2.14 times 10 to the minus 3 quantity squared divided by 1.8 exponential negative 5, and I get a concentration of 2.54 molar. Okay, so easy. All right, last topic for the course, titration. Titration is a very important chemical analytical method. In other words, in a titration, you're doing a reaction between chemical A and chemical B, and you're using what you know about the product, and you're using what you know about one of the chemicals to solve for the other. So, a couple of terms here. The standard solution, that means we know the concentration of that material. We have tested it, we know what it is. And another name for the standard solution is something called a titrant. Okay. The material that we're testing that we don't know the information about is called an analyte. And when you test a portion of the analyte, you're using what's called an aliquot. So you prepare an aliquot, and then you pour the titrant in using a burette so that you can measure how much titrant you're using. And based upon the volume of the titrant, if you know the molarity, and molarity is moles per liter, so if you know the molarity and you know the volume of the titrant, you know the number of moles of the titrant you used. And you can use those moles to figure out how many moles of aliquot you have reacted. Now, in our class, for the regular class with the COVID interruption, I love the titration lab. It's a great lab. I wish we could have done it. In fact, there were a lot of great labs in Marking Period 4 we didn't get to do. But this, if I could pick one lab to do, this would be the one lab to do with you. It's just so good in terms of learning technique and then using that technique to do the calculations. But for those of you that have signed up for AP and you have me next year, we'll be doing quite a few titrations during the year. So we'll practice it first before we do the college level stuff. But you can do a titration. We would do acid-base normally, but in the AP level, we do redox. There's a lot of different reactions. I take my orgo class, which, maybe next year. We could do a nucleophilic substitution. There's a lot of different types of reactions in which you can use the technique of titration. In fact, when they test your blood, they run what's called a titer. They do a titration on your blood to figure out the concentration of materials in that blood. All right, so for our acid base, we're going to rely on a neutralization reaction, and we would use an indicator chemical to let us know when the neutralization has taken place. All right, first of all, about neutralization. Whenever you ask students, you say, all right, well, what pH for neutralization? They always say a pH of 7. Well, that's only if you're using a strong acid and strong base. So again, strong acid plus strong base gives you a pH of 7 because look at your net ionic equation. You're producing water molecules, pH of 7. However, if you use a strong acid and a weak base, then yes, you're creating water molecules, but you're converting the weak base into a conjugate acid. So when this neutralizes, your pH is actually less than 7. Same thing if you use a weak acid and a strong base, then yes, you do produce water molecules, but you're converting your weak acid into a conjugate base, so therefore the pH is greater than 7. But you don't have to worry about that because you're not doing the lab technique right now. But, when we get to a more advanced class, then picking the correct chemical that changes color at the pH you want is very important. All right, so doing the problems on the last test, what do you need? First of all, I'll give you a balanced equation. From the balanced equation, you take the standard, you take the titrant, and you use the information about the titrant to figure out the amount of moles that you used during the titration. 3, once you know the moles of the titrant, you use the balanced equation to figure out the moles of your aliquot. And once you know the moles of your aliquot, then you can answer questions about volume, molarity, etc. All right, so last 2 problems. I'm so excited. All right, how many milliliters of sodium hydroxide are needed to neutralize a certain amount of hydrochloric acid? All right, so the first thing I ask students to do is figure out what it is that they're really asking you here. They're asking you for volume of sodium hydroxide. So if they're asking you for volume of sodium hydroxide, that makes that your aliquot, and that makes the hydrochloric acid your titrant. All right, now the balanced equation for this. We could use net ionic here. That would work, but let's go molecular because you're used to doing calculations off the molecular, not the net ionic equation. So that gives me NaCl plus water. And we're going to start with what they give us. Start with the titrant. We use 21.4 milliliters of titrant. We're going to convert that to liters. Why? Because molarity is in liters. All right, so 1,000 milliliters of HCl is 1 liter. Wow, it's been a while since we've done this. And according to the molarity rating in the problem, at 0.106, I'll stay with that color. That means that for every 1 liter of hydrochloric acid, you have 0.106 moles of hydrochloric acid. Now, according to the balanced equation, for every 1 mole of hydrochloric acid that you use, you consume 1 mole of sodium hydroxide. And according to our problem, right, 0.0947 molar, that means that we used 0.0947 moles for every 1 liter of sodium hydroxide. And then our last fraction would be, and it seems like a waste of time, but you need it for the documentation, 1 liter is 1,000 milliliters of NaOH. So there you go. So we started with our titrant. They gave us the volume. If you know the volume and the molarity, you can get the moles. And according to the balanced equation, 1 mole of acid neutralizes 1 mole of base. From there, we knew the number of moles per liter for the base, and they were just asking us to predict how many milliliters of that we would need. So 21.4 divided by 1,000, and then later on times 1,000, times 0.106 divided by 0.0947, and that comes out to be 24.0 milliliters. All right, easy. And the last problem of the year, we got 26.4 milliliters of base, and we're going to neutralize it with 21.7 mils of our standardized acid. What is the concentration of the base? All right, so what is it that they're actually asking for? They are asking for concentration, which means molarity of the base, which is LiOH, lithium hydroxide. So we want moles of lithium hydroxide over liters of lithium hydroxide. Do they give us either of these two things? And the answer is, yeah, kinda. 26.4 milliliters of the base, so we can convert that to liters. So let's start there. 26.4 milliliters of lithium hydroxide. Convert it to liters. And it's 0.0264 liters. So we can substitute that in already. All right, so now we just need moles. All right, well, in order to do this, we need a balanced equation. So we'll do lithium hydroxide plus hydrobromic produces an water and a salt. And the salt is lithium bromide. Okay, so start with what they give you. Let's start with the titrant. The titrant is the acid. And they used 21.7 milliliters of that hydrobromic acid. Let's convert it to liters. Right. And do they give us the molarity? Yes, they do. So we know, based upon the molarity they gave us, that 1 liter of that acid had 0.500 moles of that acid in it. And according to the balanced equation, 1 mole of that acid consumes 1 mole of the base. Alright, so 21.7 divided by 1,000 times 0.5 gives us 0.010. Could round it up to 9, but the new rule is you round to the even number. So for 3 sig figs, I'm rounding it to 0.08, which gives me an even number instead of an odd number. 4 moles of lithium hydroxide. And now I can substitute that in. And what's weird is that doesn't look right to me, so I'm going to check my calculation real quick here. 21.7 divided by 1,000 times 0.5. Make sure I hit the right buttons on the calculator. I did. 0.0108 divided by 0.0264 gives me, yeah, this is correct, a concentration of 0.409 molar lithium hydroxide. That's it. We're done. Thank you very much.